Hello everyone, thank you for that lovely introduction and thank you all for coming to listen to me speak. So today I'm going to talk about transitions in science. So this is going to feature my gender transition in science, but then I'm also going to talk about some of the work I've done looking at different phases and the transition between phases from a chemistry point of view. So before I start, I just want to check that we're all on the same page by what I mean by different terms. So I'm a bi-trans man. So when I say I'm bi or bisexual, what I mean is I'm attracted to more than one gender. So that includes men, women, and non-binary people. Even though there's a bi in there, it's not limited to two genders. As I said, I'm trans, so I'm not the gender I was assigned at birth. The opposite to that is cisgender or cis, which means that you are the gender you were assigned at birth. So now all about me, which is what most of the talk's about. So I was born and raised in Swindon, which is not the most exciting of places, but it is famous for the magic roundabout, which is 5 mini roundabouts around one central roundabout, and it is the reason I didn't learn to drive until I had moved away. And I came out as bisexual at 15 at school during Section 28. I then went to Oxford to study chemistry at St Hilda's College, which at the time was an all-women's college. So, and it was at uni when I started to explore my gender, expression of my gender, and I realised I was trans, which was quite difficult being at an all-women's college to realise you're not a woman. So I didn't transition officially, by which I mean I didn't change my name or start presenting as male, until I went to do my PhD at the University of York. York's very nice, it's a very supportive place to do this. And my PhD was on computer simulations of liquid crystals, confined liquid crystals. And this is where the next sort of side of phase transitions comes in. So I'm going to go through what this actually means, basically. So computer simulations, what do I mean by that? So we all know what a computer is, especially given the pandemic and the amount of time we spend on Zoom. But computer simulations is a wide range of things. So you can be looking at something as small as quantum scale, so electrons and atomic nuclei, which are sort of 10 to the minus 12 in seconds and meters. Or you could be looking at something as big as a mixing tank, or the sea, or aeroplanes, so a completely different scale of things. In the middle of that, we've got atomistic simulations, where you sort of look at the molecular level. So this is a water molecule here. Or you have what I've called mesoscale simulations. So these are where you're representing groups of atoms by blobs. So you've still got some sort of chemistry there and chemical intuition there, but you can look at much broader length scales than you can with atomistic or quantum simulations. And that's where I'm going to talk about today. So that's what type of computer model. So how do we actually do that? So in atomistic and mesoscale simulations, what we do is we represent an atom or a group of atoms as a bead with specific parameters. So over here, we're going to build a water molecule. So you can see we've got a red oxygen atom, which has a specific radius, interaction, and charge. And we've got 2 hydrogen atoms, which have different radii, interaction, and charge from the oxygen, but the same as each other because they're the same type of element. We need to put some bonds in rather than have loose atoms flying around. So we do that by joining together the beads using springs. We also have an angle potential to keep the water in the right shape. And if we've got more complicated molecules with more than 3 atoms in, we have dihedral angles again to keep the right shape and the right configuration that we expect. As I said before, mesoscale, we want to group atoms together so we can look at a larger length scale. So this is a different type of water bead representation. So here, we've got one bead that represents 2 water molecules. So we've gone from representing one water molecule with 3 beads to 2 water molecules with 1 bead. So we've got a reduction in 6. So basically using the same amount of computer resources, we can look at a simulation that's 6 times the size. So the model you use, you have to pick carefully depending on what the problem of interest you're looking at. Now we have our model. What we do is we integrate it through time, either by using Newton's equations of motions or some sort of statistical method, which technically you could do by hand, but that would be very boring. But it's the job that computers are very good at. So we do that and we see what happens basically, and we look at the phase behaviour. So the other part of my PhD was on liquid crystals. So I use the computer simulations of them. So what are liquid crystals? So you probably all have some liquid crystals with you at the moment in the form of the LCD display on your phone or on an old school calculator, if you're like me. They're also used in these sort of thermochromic paints. So here we've got a mug that's black until you put hot water in it and then a nice rainbow flag appears, or the type of temperature sensor for a fish tank. And they're also found in these smart windows, so when you have them on and it's transparent, or off and it's opaque. At a molecular level, what it looks like. So you have a crystal. These are two different phases formed of rod-like molecules. So in a crystal, you've got this periodic array where they all tend to point in one direction. Conversely, and I'll come over here for this, for an isotropic liquid, you can see they're at random and they're randomly orientated. So the term liquid crystal actually encompasses like over 80 different phases, but I'm only going to be talking about one. I'm not going to spend all my talk telling you all 80 phases, and that's the nematic phase. So you can see that in the nematic phase, they've got no orientational order. So like the isotropic liquid, they're pointing all over the place, but they tend to point in one direction. So they're all pointing up and down here. And the direction they point in is known as the director, shown here by this arrow. And if we look at them under a microscope, this is what they look like. So they're really pretty. And you can see you get this different birefringence, and then you get points like here, black points, where there's no range of nematic order, and you get just an isotropic liquid. There was one other thing that I wanted to tell you about liquid crystals, and that is if you make them with a chiral molecule or a chiral dopant, you can get a helical twist that's perpendicular to the director. So it's very hard to draw, but you can see that your director here is twisting. And this is actually the basis for how LCD displays work. So we know computer simulations now, we know liquid crystals. The final word in my PhD title was confinement. So that's the next thing. So basically, if you confine a liquid crystal, you promote all sorts of different and unusual director configurations. So here we've got our liquid crystal molecules, and then we've got some water beads at the top. And you can see that the liquid crystals are all sort of lying down at the surface. So if you do this and you confine them in a sphere, you can't geometrically have no defects. So you can't have regions, you can't have nematic order everywhere. So you can see this in everyday life. When you're brushing your hair, you get that bit at the top of your head which sticks up. It's exactly the same mathematical reason. And also like a coconut, you have the bushy bit at the top and the sort of bit with less fluff at the bottom. So if we do that with a liquid crystal, and we basically look at liquid crystal bubbles. So we have an inner water droplet, then some liquid crystal, then some more water. And this is what it looks like from an experimental point of view. So for thick shells over there, you can see we've got 2 defects, and for thin shells, we've got 4 defects, which are the black points. And we see an intermediate with 3 defects. And then we can see exactly the same using simulations. So here, I've got some of my nice results. You can see you've got 2 defects at that end, 3 in the middle, and 4 in a tetrahedral arrangement here. And the black lines show where the director's going, which is quite nice. We can also look at different types of confinement. So as well as the spherical shells, I looked at toruses or donut shapes. Unfortunately, it wasn't as tasty as this donut. So here, now instead of having the molecules lying flat on the surface, they're standing up. And if we do that, we get something that looks like this. So now we've got 2 defect rings. I'll come back over to this side. Sorry. We have 2 defect rings, one going around the center and one going around the outside. So now if we put some chiral dopant in and we cause that twist perpendicular to the director, what we see is we join up our defect lines. So now we've got 1 defect that goes around the center twice. And if we keep going, we can get 2 interlinked rings, and keep going and we can get a trefoil knot, and so on as you increase the chirality. So that was my PhD in 4 minutes, basically. So then after my PhD, I had a year out of work for health reasons. Quite a lot of it was related to transitioning. And I also spent 6 months in Northern Ireland. I then moved to Sweden for a year, to the Swedish School of Textiles in Borås, which is a very small city just outside of Gothenburg. But it does have a very nice mural of the Nobel Prize on it. And when I was in Sweden, I went back into the closet about being LGBT. So I did this for a couple of reasons. So I was in the UK, I knew what the climate was like about being LGBT, and I knew what law there was to protect me. But going to a foreign country, I had no idea what this was. But the thing I did know about Sweden is that sterilisation was required for trans people until 2013. So if you wanted to transition in Sweden, before 2013, you had to be sterilised. And since I was only there in 2015, I was not sure what it was going to be like to be over there. And actually, that was quite difficult going back into the closet, which obviously I'm not now. So then I came back to the UK, and I went and did a postdoc in Cambridge in the chemistry department before going up north to Manchester for nearly 4 years into the chemical engineering department. And now I'm going to talk to you about some more chemistry, so it's not all just about me. And I'm going to talk to you about shampoo. So this was some work I did with Unilever, who make all these shampoos. And they were interested in shampoo because they want it to be the correct thickness. So they don't want it to be too thick, so you're rubbing basically a block of rubber into your hair. And they don't want it to be too thin because then it just runs out your hand. I'm interested in shampoo for a related reason. So firstly, it's a non-Newtonian fluid. So that means if you apply a shear to it, its thickness and viscosity changes. It actually gets thinner. So this is why when you have some shampoo, it looks quite solid in the bottle, but you can still squeeze it out of the nozzle. And the reason for that is it has a microstructure. So the molecules self-assemble inside the shampoo, something like this. And that microstructure is history dependent, so it depends on how the shampoo is processed. So I did computer modelling of this. So this is my computer model. So this is a surfactant. So a surfactant has two parts. So it has a water-loving head group or hydrophilic head group and a water-hating or hydrophobic tail group. This molecule itself is SLES, which I would put money on. If you picked up a bottle of shampoo in your house, it would be the second most ingredient after water. And the interesting thing about SLES is that it's got a negatively charged head group, which means that its properties change with salt concentration. So this is the type of bead that I was talking about earlier with the coarse graining. So this is an experimental result from the literature. So on the y-axis, we've got the viscosity or thickness, and on the x-axis, we've just got salt concentration. So the amount of SLES present in this graph is the same. It's 10%, all of it. But you can see you get a huge change in viscosity from nearly 0, so about water, all the way up to nearly 30, which is a massive jump, just by changing the amount of salt you have present. And what we could do is, using computer simulations, we can relate this change in viscosity to the microstructure. So if we look at that at low salt concentration, what we see is these discrete spherical aggregates of micelles. So these are still quite small, so they can move past each other very easily, and you've basically got the viscosity of water and the surrounding medium. Then if you increase your salt concentration, this means that the repulsion between the negatively charged head groups decreases and they can pack closer together. So the micelles start to grow in 1D, so you get these sort of short rods and short worms growing. And as you increase the salt, they grow longer and longer until you're right at the peak, where they're orders of magnitude longer in one direction. So they're still nanoscopic in the two directions, the short one, and they're on the order of microns in length in the other direction. So this drastically increases the viscosity, and the best analogy for this is pasta. So if you've got a bowl of spaghetti and you try and pull one string out, it's very difficult, all the spaghetti comes with it, which is not necessarily a bad thing, but it does mean that it's much thicker viscosity for that bit. If you continue to add salt some more though, the viscosity and the thickness comes down, and that's because you get these branches forming. So this gives the mixture different ways of relieving the stress from shearing it. So now the branches can slide along one another, and you also get this phantom crossing where you get two micelles come together, they form a branch, and then they move out away from each other again. And I thought you can't do a talk on simulation without showing a simulation. So I've just got two examples here of a low salt concentration and a high salt concentration. I've started it off in this tube, basically. So there is water and salt in here, but you can't see them because if I showed them, you wouldn't be able to see what the surfactants are doing. And if I hopefully press play, you should be able to see what happens. So at low salt concentration, they all move around and they break up, and you see these spherical micelles forming. Whereas if I do it for the higher salt concentration, There we go. Hopefully it starts, they're moving, and basically that will just keep going on for however long you run the simulation for until you get bored. So then in December last year, I moved to Exeter. So I haven't got much on this slide yet, but I'm very excited to meet you all. And I'm really enjoying it down here. And I'm hoping to be able to do some more work on computer simulations of these phased behaviour systems. I need to thank the people who helped me with this work. So my PhD supervisor, Martin Bates, and one of the postdocs on the project, Martin Walker, at York. And then the work done in Manchester was done with Maria, who is she was a PhD student. She's now up in Edinburgh doing a postdoc. And my PI was Paola Carbone. And in general, the multi-scale modelling group in Manchester were very supportive and gave me a lot of ideas, and I couldn't have done it without them. And finally, thank you to you for listening and being a really good audience. And yeah, any questions?